Okay, gang. The next thing we want to talk about, we said the next video would be the next application of the exponential growth and decay, well, actually the exponential applications. The first one we saw was with the compound interest formula, when the interest was compounded a finite number of times, right? Then we said what that would lead to if it was compounded continuously. That was that formula A equals P e to the RT, or PERT. Remember, E is the natural exponential number, okay? Or the natural number, rather. Okay, the next thing, gang, is this exponential growth and decay. This is the next application, okay? Now, I used a little bit of calculus symbolism, and that's okay because all of you have indicated you're going to go on to calculus anyway, so it's not going to hurt to see this. I want you to take a look at this equation, okay? And here's what this equation says to us, and some of it harkens back to our work in Algebra 2 when we studied equations of variation, okay? The symbol on the left-hand side, that's the calculus symbol. But here's what it says in words, okay? It says that the rate of change of some quantity with respect to time, okay, that's what the little t is, the rate of change. And when you get to calculus, we spend a great deal of time studying rates of change. You'll see, okay? But this says this says the rate of change of some quantity, capital Q. So that quantity could represent the colony of a bacteria, population of a small island. It could represent a radioactive substance, the amount of grams, we'll say, of some radioactive substance. It could represent the initial amount, or it could represent the amount of money in an account, a bank account, after a certain amount of time, like we saw in the previous video, okay? So, the rate of change of some quantity with respect to time is proportional to the amount of that quantity present, okay? Any function, gang, that adheres or satisfies this equation is called an exponential growth or decay model. Its solution, which can be found using calculus, is equal to this function right here, okay? This is a model. It's called an exponential growth and decay model. Its solution is this function right here. Q of t, that's the quantity, okay? T represents time. The time could be in seconds, minutes, months, years, whatever. It depends on the context of the problem, okay? Q sub 0, that's the initial quantity. And unless there's a reason to say otherwise, gang, when we say initial quantity, we mean when time t equals 0. So 0 seconds, 0 minutes, 0 year, whatever, okay? This is the principal or initial quantity. K is the growth or decay constant. If K is positive, then we have exponential growth. If K is a negative number, then we have what we say exponential decay. Exponential decay is an example of that. Some of you are in chemistry right now. You've seen radioactive isotopes decay exponentially, okay? And T, of course, represents time. E is the natural number, 2.7, 1828 roughly, okay? And we say then that this is the solution to this exponential growth and decay model, okay? So a lot of your homework problems are going to be looking like this. They're going to give us information. Depending on the context of the problem, we plug everything into this. And then, of course, there's certain things to solve, which we'll see when we go through the examples, which I mentioned before. We'll probably use pen casts for those. Okay, let me just mention one other thing. There's a couple of things I want to mention, actually, but the first is this. There's nothing special about the letter Q, okay? You can use capital N if you want. Like your book uses capital N. Some books use capital A, for example. There's nothing special. It's letters of the alphabet, okay? I'm just saying Q for quantity, okay? And there's nothing special about that either. The other thing I wanted to mention is this. Okay, I said it a moment ago, but just to emphasize the point, when K is a positive number, we have exponential growth. But if it's negative, we say we have exponential decay. Okay? So remember from our work in section 6.1 when we were talking about exponential functions, their graphs and their characteristics, right? This expression right here, what would exponential growth look like from here? Exponential growth, gang, would look like this. Okay, that's what exponential growth would look like. At t is equal to 0 seconds or 0 minutes or whatever, if t is equal to 0, again, you're going to have e to the 0 power, which is equal to 1. 1 times the initial quantity is just the initial quantity. That's your y-intercept. Okay? That's what exponential growth is going to look like. Notice that it keeps rising forever, though. Sometimes that's why this is referred to as uninhibited growth. Okay? Now, practically speaking, is that going to happen depending on the context of the problem? Most likely not. Right? We would expect the population to level off, for example, the population of a small island, or like if you're looking at E. coli in a little petri dish or something like that, the number of bacteria in that dish can't grow forever. They're going to run out of room, resources, they're going to be eating each other, all that kind of stuff, right? So we would expect the population to level off. In the case of exponential decay, the graph would look like this. Okay, so for example, radioactive isotopes or something like this, okay? So we've got these scenarios right here, and then I think it would be instructive, again, because there's two special times that come up pretty often, one for each of these scenarios. The first one is called the doubling time, right? So in the case of exponential growth, the doubling time is that time that's necessary for the initial quantity to double in size. Whereas for exponential decay, the special time is referred to as halving time. Halving time is the amount of time necessary for the initial quantity to decrease by 1/2. Those of you in chemistry have heard of this. You refer to it as half-life. Okay? So what I want to do is I want to solve for those two special times because they come up so often, it's probably worth it just to get them out of the way one time for all time. Okay? Again, just for our purposes, so we can call it something and set it aside as something special, let's refer to the doubling time as t sub 2. Okay? And when the time comes, we'll refer to the halving time as t sub 1/2. Okay? All right, so here's what I'm going to do. By our definition, the remark we just made a moment ago, this is the amount of time that's necessary for the initial quantity to double in size. Okay? So I'm going to take that time, that special time, and I'm going to force it into this model over here. Here's what that's going to look like. Okay? Now, after that amount of time, right? After that amount of time, how much of a quantity is present? Double or twice the initial quantity. So the left-hand side should be this. Okay? Now, here's what we want to do. We actually want to solve this equation for t sub 2. Actually find it outright. Okay? All right, so next thing I'm going to do, I'm going to divide out the initial quantity from both sides. Divide both sides by q sub 0. Okay? Okay. Now, this looks like the kind of problems we were solving back in section 6.3. In fact, okay, the equivalent logarithmic equation for this exponential equation should be this. Okay? Remember, we didn't solve it just yet. We just replaced one equation with an equivalent equation. But look, okay, all we have to do now is divide out the rate from both sides. Okay? So, one time for all time. In an exponential growth model, the amount of time it takes for an initial quantity to double in size is given by this little formula right here, gang. It's a calculator thing. It's the natural log of 2 divided by whatever the growth constant k is, whatever the growth rate k is. Okay? Notice at this step, gang, right there, at that step right there, we divided both sides by q sub 0. What does that mean? That means that that special time has nothing to do with the initial quantity. It doesn't matter, for example, suppose that this was a compound interest problem. Instead of this, it would look like PERT. But remember, there's nothing special about the letters that we use for the initial quantity, whether it's P or Q sub 0. What this says is the amount of, under those circumstances, the amount of time necessary for your money to double in size doesn't matter how much you start with. It's given completely by this right here. Okay? In terms of the compound interest formula, compounded continuously now. Again, look at the formula. Look at the formula. It's the same as this one right here. Okay? So over here, the time necessary for the initial quantity to double in size, your principal amount now. Same formula. Okay? So what I was going to say was, for example, in the case of money, it doesn't make a difference if you go into the bank with $500 or $5,000. The amount of time it's going to take for that money to double in size has nothing to do with that, and everything to do with the rate or the interest rate itself. Okay? So that's an example of exponential growth and the special time associated with it necessary for an initial quantity to double in size. Now here's what I want you to do. I want you to solve for the decay, right? The decay instance, the halving time. Here's what you do. Start again. Okay, you're going to have exponential decay. Let's call the halving time t sub 1/2. Okay, t sub 1/2. Now here's what you do. You take that special time, you force it into this expression here. What's the halving time? That's the amount of time necessary for the initial quantity to decrease by 1/2. Find that. I want you to do it yourself. Don't look in the book. Try it on your own. Show this, okay? Don't take my word for it though, gang. I want you to fill in the blanks. Show that you can repeat this whole process and come up with this value right here, okay?